Welcome to the Wisconsin Podcast. I'm Craig Sauer. On this podcast, we talk Wisconsin things, everything from media, sports, culture, nature, politics, and more. This week, I feature a conversation with Jim Lattis about Wisconsin's contribution to the field of astronomy. Lattis holds a Ph.D. in the history of science from UW-Madison and is the author of many publications in that field. He helped create UW Space Place, the outreach and public education center of the UW-Madison Astronomy Department, and has directed it since its founding. He manages the historic Washburn Observatory. He teaches courses in introductory astronomy and its history, gives frequent public talks, and consults widely for the media. He has also led trips focused on astronomical tourism. I talked to Lattis last December at the UW Space Place during an important week that marked the 50th anniversary of one of the biggest achievements in Wisconsin astronomy history, the launch of the Orbiting Astronomical Observatory 2, known as OAO-2, which was the first successful space telescope launched in 1968. A piece of equipment developed at UW-Madison was aboard the OAO-2, which was a precursor to other space telescopes, such as the Hubble. This week is a kind of a special week for Wisconsin astronomy because of the connection to the OAO-2 project, which I want to talk about a little bit. But I thought I would kind of lead up to that by asking about Wisconsin's place in astronomy history in the 1800s and early 1900s. And can you just kind of elaborate on Wisconsin's place as you see it in astronomy history?
Sure. Right. Wisconsin has been the home to two really important observatories in the 19th century. At the end of the 19th century, early 20th century, Washburn Observatory here at the university, which was effectively started in 1879. That's when the telescope was installed there. It wasn't quite done for a few years after that. But by 1900, let's just say, there was the University of Wisconsin had one of the major research universities in the United States. Not the biggest or anything along that line, but important in terms of its scientific activity and reputation. And its place in the astronomical world. That was about the time that the American Astronomical says that the professionalization was beginning to happen in American astronomy. And Washburn Observatory and its personnel played a big role in that. And then the other one was, of course, in Wisconsin, the Yerkes Observatory, which was established by the University of Chicago, but on the north shore of Lake Geneva in Wisconsin, because of sort of logistical reasons. They wanted something away from the city, but not too far away, because you didn't fly across the country in those days, of course. So you needed a reasonable train ride away, and that observatory right away was the largest refracting telescope in the world and still unsuperseded in that respect. So it was a major institution immediately, also because of the attachment to University of Chicago, and it was a major research establishment by its very foundation. So those two and became very important, especially it was a little bit later coming on to the major scene. It was a major and active observatory, and again, played a key role in this professionalization that I mentioned. But it sort of came into prominence, especially in the 30s, as it became one of the homes of what we now call astrophysics, the sort of a move away from traditional astronomy. That was happening here at Washburn Observatory too, but with a much smaller staff and in a much more narrow and highly specialized area. And University of Chicago was one of the early ones. I should say Yerkes Observatory was one of the early ones to develop parallel observational and theoretical departments, so to speak, specialties in modern astrophysical problems. Yerkes Observatory, by the late 1930s, looked like what modern research observatories look like now. They had a big reflecting telescope that their staff had access to. They had important theoretical research programs going on, and the two complemented each other. The people who were running the institution saw to it that the people who did that the theoretical and the observational programs work together in a way that produces solutions to interesting scientific questions. Well, that's a kind of a generic description, but that pattern really started to emerge there at Yerkes Observatory.
What were some of the interesting or important findings or research that was done at Washburn, just out of curiosity?
Sure. So in 1879, what's still the big refracting telescope there, the 15.5-inch refractor, was installed there in 1879. A standard pattern in 19th century observatories was to have a telescope like that's usually called the equatorial telescope, which really just means it's a big telescope you can point anywhere in the sky. And then another telescope was pretty standard, an instrument called a transit or meridian circle telescope, which was specifically designed to do accurate position measurements on the sky and could not point just anywhere, which is why it's called a meridian telescope. It could only point along the meridian. And that tells you a little bit about what astronomy going into the early 20th century was like. That is, it was still heavily concerned with the determination of position measurements on the sky. And that served a couple of different research goals. One is what are called the proper motions of stars, which means they're actual motions through space, which are, of course, very gradual. You have to measure very carefully to see that happen, even for nearby stars from year to year. Another one is parallax motions, which give you the distances to stars, and measurements for both of those kinds of things would have been done with the meridian circle telescope. And then measurements of, if we're talking just about stars, the equatorial telescope was used to measure the motions of binary star systems, of two stars that visibly orbit around each other. And when you put all those things together, you begin to get a handle on the nature of stars. Stars were tricky objects. Are they all the same brightness, or do they have different brightnesses? How far away are they? What are the systems of stars like when there's more than one? How are they interacting? So you begin to have a whole lot more physical insight into stars and stellar systems. And that comes in part out of that early combination of those two kinds of telescopes. That's one of the reasons, one of the ways in which those two things were working together. But other stuff that was really important here at Washburn sounds intensely boring if I start telling you about it. For example, understanding the refraction of starlight as it passes through the atmosphere, because the only way you get an effective position out of your meridian telescope is if you understand how the light from a star might be bent as it passes through the atmosphere. Otherwise, you're not measuring its correct position. Another one is something called the aberration of starlight, which is another apparent change in the position of stars, in this case owing to the motion of the Earth in its orbit around the sun. And it will shift the apparent position of a star. So if you're not correcting for things like that, then you're not getting accurate positions. And the positions you want because of parallaxes, which get you distances, and that's back into the interesting stuff. But you've got to do the boring stuff, and there were major programs here using that meridian telescope to establish the constant of aberration and the refraction of the atmosphere. So those things were going on as well. As I say, boring but foundational thing, absolutely essential things that you have to master if you're going to proceed on with the more interesting stuff. So all that was happening here. Decades of double star observing. With the same telescope, in fact, by the same astronomer, measuring double stars using the same instrument for decades. It's not clear that it's true, but it was considered an advantage anyway, that you had the same telescope, same instrument, same observer doing this night after night after night, year after year, that this might give you better positional data on these things. Almost all the things we talked about were rendered obsolete by photography. Photographic techniques took over positional measurements of stars, and the position measurements of binary stars, those began to be recorded photographically rather than the visual measurements that had been made. Those early years of those positional measurements, and then the much more prolific photographic analogs to those made it possible to open up new fields of astrophysics and really understand stellar physics. And that's probably the most important thing in terms of at least astronomical knowledge. It's a major piece of human knowledge that 150 years ago would have been a complete mystery. What are those things you see in the sky every night? How much are they like the sun? How different are they from the sun? Questions like that had basically no answers 150 years ago, and now we can say we understand quite a lot about those things. So that was a big deal. That kind of astronomy and some of those that foundational work was happening here. And then I did allude just briefly to photoelectric astronomy, but I'm going to let myself take a breath in case that's not what you want to talk about right now. But that's another one of these sort of early astrophysics, like the spectroscopy that they were doing at Yerkes, that really made modern astrophysics possible.
Well, go ahead and talk about that a little bit. Why was that important? How did that contribute to astronomy?
Foundational to all these things, kind of like as foundational as star positions, is to say, well, how relatively bright are the stars that we see in the sky? This basic business, which is called photometry, it's what astronomers call this quantitative measurement of the intensity of a light source. There were ways to go about it, but the errors in the methods were very large and depended always on the human eye or on photographic plates, which turn out to be nearly as hard to deal with as the errors in the human eye, although maybe not quite as bad. At least it's reproducible with photographic plates. But the astronomer who came here as the fourth director of Washington Observatory, a guy named Joel Stebbins came here from Illinois, at the University of Illinois, where he had spent a few years there, close to 20, working with some early electrical means of measuring starlight. Basically what happens is if you allow light to fall upon certain types of metals, potassium is an excellent example and was used widely for this, the light that falls on it will release electrons, essentially eject electrons out of the surface of the potassium. So if you design a tube, let's call it a vacuum tube, although they weren't always vacuums, that had potassium inside there, and you let light fall in there, there'll be electrons free. You can, if you charge your potassium metal negative and put a positively charged plate in there nearby it, then when you shine light on it, current will flow across that, and you'll get a number of electrons, which is directly proportional to the amount of light falling in there. So you can measure the electrical effect. Electrical effects are easy to measure, relatively speaking. So now if you get twice the signal from one star than you do from another star, then you know that it's twice as bright because you got twice as much light. You got twice as many electrons from that star as from that star. Stebbins had just started working with that technique, had worked with it for just a few years there at Illinois when he moved to Wisconsin, became director here. And he brought that technique with him. And the first problem that they worked on and would work on for decades were eclipsing variable stars. So this new piece of information, how the light varies in an eclipsing variable system, was what yielded the actual dimensions of the stars. It turned out that this photoelectric photometry method was applicable to a bunch of other interesting problems, and Stebbins continued to find other applications for it. Perhaps the most important was that he was able to use photoelectric photometry to demonstrate that there is interstellar matter. When we look at a star, we're not just looking through transparent space, that there's stuff between us and the stars, which affects the light. In particular, it reddens the light. And he was able to adapt this photoelectric photometry to color measurements, quantitative color measurements, and map this interstellar matter and figure out what its distribution is in the galaxy and how it varies in a three-dimensional sense. It's deeper. Looking at a more distant star, you're looking through more of it, so you can get some idea of the three-dimensional distribution of this stuff in the galaxy, which was something whose very existence was controversial until that time. In fact, there are still astronomers in the 1920s, even up to about 1930, maintaining that this is insignificant, that space is basically transparent. But it isn't. And you get wrong numbers when you start calculating distances of things if you haven't taken into account the absorption from this matter. And Stebbins had figured out how to do that. So that was very important work, again, coming out of that same technology, just a different application of that technology. So that kind of thing was developed here and then used not only at Washburn Observatory, but very quickly afterwards. Stebbins himself started using the big telescopes at Mount Wilson in California, for example. So he carried that work quite far by the time he retired in the late 40s, and his students carried it on. And that kind of thing now is still done, but just routinely. Every pixel on every chip is doing photometry these days. So nowadays we do massive parallel stellar photometry every time they take an image of something in the sky. But that started here with those astronomical applications that Stebbins, again, starting in the early 1920s, about 1922 and on.
So a lot of that early, if to characterize it a little bit, correct me if I'm wrong, but that a lot of that early research in Wisconsin really went a long way in our understanding of the scale and kind of dimension of space.
Very much. Yeah, right. Because you can't get that number without taking into account this interstellar matter. And that's what they were working with here. The Wisconsin astronomers really were the only ones who had the means to measure those effects. So that's very, very much something that comes from here. Up until about World War II, nobody was as successful as applying it as Wisconsin astronomers. But it became an industrial technology. By the 1950s, it was off-the-shelf kind of equipment. So it became applied much more widely after that. So it's not as unique to the science we were doing here, but the science at Wisconsin continued to depend on those kinds of studies. And that brings us really kind of around to the Orbiting Astronomical Observatory, because it was the foundation of technological and scientific work here that made it possible for the University of Wisconsin to build space-based instruments.
Yeah, so fast forward, it's 1968, the launch of OAO2. What is OAO2, and why was that an important project that Wisconsin contributed to?
So OAO is Orbiting Astronomical Observatory, which was a series of spacecraft that NASA planned and ultimately launched in the late 50s. There were a number of astronomers who were really interested in this, but they were the minority among astronomers who were willing to start dealing with the technologies that were required and the operating conditions that were required and the standards that would be imposed on an instrument that's going to be launched into space and has to keep on working. But one of those astronomers who was very interested in that was Arthur D. Code, who had actually gotten his Ph.D. at Yerkes, then had worked here at Washburn for a little while. So he was a thoroughly Wisconsin astronomer, and he knew the kind of photoelectric photometry that was being done here. Although by then he was out at Caltech. By then, I mean basically 1958. Code could see that what you needed to do was photometry from space. So he came here with the understanding. He became the next director of Washburn Observatory with the understanding that Wisconsin would go in this direction. And NASA designed, or really contracted to Grumman Aerospace, this series of satellites called the Orbiting Astronomical Observatories. The first one was a huge failure, but there was a Wisconsin payload of instruments on the OAO1, which reached orbit, but then failed almost within hours of being switched on. This was common in the early days of space instrumentation. People had not quite figured out how to make, say, high voltage power supplies that would work in a vacuum, which is odd because they've been doing that on the ground for a long time, but space just presented these challenges. And the OAO1 was a total failure. And NASA decided to do a second one, and they asked Wisconsin to build a second, basically a duplicate of the thing that they had built before. And they launched it along with an instrument that had come from the Smithsonian Astrophysical Observatory that was planned to do ultraviolet imaging. Those two instruments were paired on this next attempt at an OAO, which became OAO2. And was so successful that people pretty much forgot about OAO1, which, as I say, was a huge embarrassing failure. But OAO2 was great because it operated for way more than the nominal 1 year. If it operates for a year, we declare success. But we don't go home, it turns out, because they extended, NASA continued to operate it through February of 1973. And it was enormously productive scientifically, and most of that science came out of the Wisconsin experiment, which was much more successful than the Smithsonian. And so most of the good science that people point to from OAO2 came from the Wisconsin instrument. And that was a big deal, the first space observatory. It wasn't that it was the first astronomy done in space, but it was the first sort of general purpose instrument where somebody could say, oh, well, now that we've looked at these stars, that presents some interesting questions about this other group of stars or other type of object or something. And you could come up with a new plan and then go observe that with your general purpose observatory in orbit around the Earth. So that's a kind of thing that the Hubble Space Telescope and other space observatories do now all the time. OAO2 was the one that really showed that was possible. And that the astronomical community could find more than enough things to keep a space observatory busy. The very famous finding was that comets have a vast cloud of ionized hydrogen around the nucleus of the comet, which turns out to be water. You're seeing the hydrogen from dissociated water molecules. And comets have been suspected of being icy bodies before, that when they warm up as they come in close to the sun, they begin to vaporize, and that the cloud of stuff we see is a cloud from some kind of ices. But just what the nature of those were and the proportions of what they were was a subject of some speculation, and this showed that they're mostly water. So our current understanding of comets that comes out of that OAO data and feeds back into what people think about the formation of the solar system. That means you had to have somewhere in the early solar system for these icy bodies to form, and by some process, they've ended up in this vast reservoir, which we usually call the Oort cloud, way out there, and they occasionally come in. Fortunately, a couple of them did during the time the OAO was in orbit, so that they could see these, and those weren't anticipated at the time of launch. So once again, you've got this general purpose observatory that you can turn to look at whatever turns out to be interesting. Well, this list goes on, but those are the sorts of things, important scientific results that came out of there.
What do you think 50 years later, what's the strongest legacy of that project? Was it the fact that it allowed people to do Hubble, to go forward with that? I mean, it was a precursor, right? So what's the biggest legacy you think 50 years later?
Well, I mean, I think it falls into different categories. Understanding stellar physics is just so fundamental to the way we think about the universe. Scientifically, that's probably the most foundational thing. But another category is precisely what you said, that you can operate a facility like this on the long term, and that important scientific results can be obtained that way. And that model isn't just the Hubble, of course, but the other many of the other instruments that operate now. Yeah, that they're following directly in that pattern that was established with the OAO2.
So fast forward to today, what is kind of the status of the UW Astronomy Department? What are we up to here in Wisconsin, and kind of where is it? What's its place in the larger just astronomy field?
We're definitely one of the foremost astronomy departments in the U.S. I don't know how it's ranked, but some of the things that you see in the current research that the department does now has really clear roots going back. A big specialty here is interstellar matter, which is now called the interstellar medium, and is broadened now not just into the matter, not just the dust and the gas that's out there, but the way they interact with magnetic fields and radiation and all that kind of stuff. The whole understanding of the interstellar medium, which is important in a bunch of different contexts, everything from star formation to galaxy evolution. That's a major specialty here, both at the observational and the theoretical level. I mentioned earlier that Yerkes, I mentioned that pattern that they began to have sort of interacting theoretical and observational programs. That was something that didn't happen here until about the 60s. We continued to be heavily observational. The first theorist wasn't hired here until very late 1950s and early 60s. That's when that side of the department started to develop. But these days there are other completely unforeseen, in those days, approaches to astronomy. For example, massive numerical computing. So trying to understand what happens to galaxies as stars interact at the level of gravitational interactions, and then the interactions with the other stuff that we know out there affects all that now, the dark matter distribution and interactions with other galaxies. That's a big strength here as well, numerical modeling, so to speak, although that term seems a little vanilla compared to what they're really doing. This massive, they're using graphics processors, which are designed, of course, to compute gazillions of pixels, but it turns out you can apply them to massive collections of objects as well, as if you were manipulating pixels, and adapt that to physical models of things. So that's a big area that has no precedence. That's a new thing, a very new sorts of thing that's a strength here. Another thing that goes back, though, is we're very big in new instrument design and fabrication. So, for example, we have two large ground-based telescopes, one in Arizona and the other in South Africa. And astronomers and engineers here at Madison design and build cutting-edge instruments for these things. For example, instruments that use fiber optics to create not just the spectrum of one object at a time, but the spectra of dozens of objects at a time. So you can distribute optical fibers over the image of a galaxy in your telescope and simultaneously get spectra from near the middle and around the edges, whatever distribution you want, which gives you then not only compositional but also dynamical information about that galaxy. And you get those all at once if you've done this effectively parallel spectra processing. But anyway, there are a number of areas in which the department has a great reputation in innovative research.
As we were talking before about the Washburn and the Yerkes observatories, which I guess by now have been are basically outdated. Can you tell me a little bit about what the fate of some of these observatories that were built? What can we do with them now?
Yeah. No, it's an excellent question, and one that gets asked a lot these days. As we speak, what will happen at Yerkes Observatory is still up in the air, as far as I know. This is not unprecedented, and other observatories have sort of different stories of one sort or another. Lick Observatory, which was in many ways almost a sibling of Washburn Observatory, many links between Washburn and Lick, which is on Mount Hamilton in California, outside of San Francisco. The University of California concluded a few years ago that there was no point in maintaining this ancient mountaintop observatory, and it wasn't producing research results on a par with what they could be doing if they were spending that same money, on telescopes on the top of a mountain in Hawaii or something. And they wanted to shut that down. There was a public outcry, I guess you could call it, that the life of this historic observatory ought to be extended, even if it couldn't be a research facility. And the University of California managed to find some other functions for it, and so far they've been keeping it going. So it's still within the University of California system. When something similar happened at the Mount Wilson Observatory in Southern California, where what was the largest telescope in the world for a good while, the 100-inch telescope and a large 60-inch telescope were there. lots of links between Mount Wilson and Yerkes Observatory, because Mount Wilson was where George Ellery Hale, basically the guy who started Yerkes, that's where he moved to. Mount Wilson went a sort of different path in giving up its role it's sort of forced out of its role as a research observatory by its proximity to Los Angeles. The sky there is practically makes research astronomy anyway practically futile. But they're in the process of transitioning into an educational and historical institution there that operates kind of like a science museum. So people pay fees to come up there and visit the place, but also they sell observing time out there. It remains to be seen whether this is a long-term sort of model. But Yerkes may be going a similar sort of way, because the University of Chicago, like the University of California, doesn't want to deal with it, and for the same reasons, because it really isn't a successful research institution anymore. And so trying to find the way towards its use as a historical and educational institution, that's the challenge. It has the advantage, Yerkes, that is, of proximity, I guess like Mount Wilson, proximity to a big population center, unlike Lick, which is an hour and a half drive up a mountain. But they're trying to figure that out at Yerkes Observatory. So all of these big observatories have that problem. They cost a lot of money to keep up, but they're also historically really important, and they're also valuable educationally. And so I hope we find ways to that. Smaller observatories like ours, which is right on the university campus, are not so expensive to keep up. In fact, it costs very little to keep ours operating. It wouldn't simplify things much to remove the telescope from that building or something. And so it hasn't had the kind of challenges that a major mountaintop observatory would have. And we've been pretty successful. It's still popular with people, and we use it for educational purposes, which is great because it's right on campus, again, as opposed to, having to drive a long way to Yerkes or something. So we've had pretty good success, but other universities have made other sorts of decisions. There have been plenty of them that have been junked in varying degrees. A fairly recent one, an East Coast college not so long ago, decided that they didn't want their telescope, but they didn't want to get rid of the building. They wanted to keep the building because the dome itself is such a landmark on the campus. So they're not going to build a new building there, but they wanted to use the considerable volume inside the dome for something other than a telescope that nobody used. So this relatively large refractor, like about a 20-inch refractor, was kind of looking for a home. And a lot of us were kind of worried about the direction that might go, but a rescue came in the form of the Waltons of Walmart, who agreed to take this telescope and build a new observatory for it in Arkansas, for, of course, not scientific really, but for educational and historical purposes. So that was sort of a white knight riding in with lots of money to rescue that telescope. And now that university will get to remodel their building for whatever their uses are for it. That's maybe not the best solution to separate the telescope from the observatory, but it's at least better than seeing either of them completely junked. So the smaller observatories will have these sort of unique situations, each in their own place, and we certainly use ours. The Washington Observatory, since April of 1881, was when the policy of being open to the public on the first and third Wednesday nights of the month, weather permitting, that was established by the second director of Washington Observatory, and that's something that we still do, and it's very popular. We have lots of people who turn out at the observatory on the public nights to peek through the telescope at a bright planet or the moon or a double star or whatever it is that's available that evening. It's quite popular. And again, it's successful. We use it for our intro astronomy classes too, so it has educational applications. So I think Washington Observatory's future, I hope, is fairly secure, but it is the problem is of antiquated observatories at sea level is not going to, or even the ones on the mountaintops like Lick, but those problems are going to keep on going as the research moves away onto bigger telescopes or into space or whatever happens there.
When some of these facilities are announcing their closure, there's, like you said, there's some public outcry, or there's a lot of interest in the public's access to these facilities. What do you make of that people have an interest in things like that? What does that say to you?
I mean, it's just further testimony to me that astronomy is something that the people are interested in. It's not a subject that has to sell itself very hard. It's kind of a romantic idea to look through this big telescope gazing out into the universe. Just at the descriptive level, it has an appeal. Pretty much any telescope, compared to some other scientific instrument, has a very long lifetime, a long, useful lifetime. So Yerkes Observatory, up until they stopped doing research just a few years there, could take a photograph of a globular cluster, and they could go into their photo archives and compare that photograph with a photograph of the same globular cluster taken over a century before. That kind of continuity, a little bit like George Comstock's having observed double stars with the same telescope, same instrument, same eyeballs for decades there. That long scientific usability of telescopes and observatories automatically gives you a little bit of a sense of the people who used this. Oh, gee, Einstein visited here, or these great observers discovered this or that. Edwin Hubble got his Ph.D. at Yerkes, just like Art Code did. And so these things are more engaging to people, both because of the subject matter and because of the long lifetimes that they have, the long heritage that they kind of build up almost naturally. So it doesn't surprise me at all, and it's a good thing. In the local community there at Yerkes has been the driving force to see to it that observatory is treated properly, even though the University of Chicago wants to let somebody else take care of it now. So that's very encouraging, and I hope we'll always see this mixture of historical interest and popular interest, but also educational applications. And somewhere along in there, I hope all these historic observatories can find a path to stability.
You brought up something interesting, which was that the Washburn Observatory has always been, in some sense, open to the public. And that maybe speaks to why we're recording this interview at a place called UW Space Place. Why is it important to do outreach? Why is it important for this to be, accessible to the public, and for the UW of Wisconsin Astronomy Department to be a public-facing entity in a lot of ways?
Because science literacy in a society, this kind of brings us back to flat earthers, maybe. It's not an obvious thing for most people to understand why we have drawn various conclusions about the world the way we have. And the process by which scientists go about testing ideas about nature is one that you really only have insight into if you've been educated in a particular field. And of course, it varies from field to field. But if you don't have much of a background in science, then what you pretty much have learned are usually the results of these things. Oh, they tell us that the Earth is this old, or whatever. Jupiter has that many times as much mass as the Earth, or whatever. It looks like a whole lot of facts. It's kind of what the phrase "body of knowledge," which sometimes worries me, is sometimes people think of that as science, that's what science is. But more importantly, it's a way of generating ideas about nature and testing those ideas and differentiating the good ones from the valuable ones from the less valuable ones. That's a hard thing really to teach, but it's really important because the knowledge that we do gain from science is one of the reasons why life for us is so much different and so much better in so many ways than it was for almost all of our ancestors. And we need to keep on doing that. But you need to have an educated public that understands something about how science works, as well as something about what science teaches about the world. So we try to do that. to a certain extent here. And astronomy, of course, is our particular area because we're the astronomy department. But I think we have a responsibility to take the lead in that because of what we were talking about a few minutes ago, that there's a certain amount of intrinsic interest in astronomy. Everybody encounters at some level or other the astronomical phenomena, the astronomical facts of life that we have all around us, summer and winter. So we have kind of an opening there that allows us to represent science more broadly. And we try to do that here at Space Place. So not all of our programs and things are very strictly astronomy related. But that kind of science outreach does have a long tradition here at Madison and is related to, actually predates the whole Wisconsin idea. And it's an important tradition that we try to follow and build where we can. So so Space Place is very much in the spirit of those public nights at Washburn Observatory.
Can I ask how you got interested in this field originally? What kind of created the interest within you?
I was growing up in the days when, John Glenn was. I was pretty entranced by that and watching the television, these rocket launches and these astronauts and all this kind of stuff. And it was probably that triggered my interest in astronomy, which wasn't necessarily a connection there. I mean, the space technology and riding rockets into space and that kind of stuff doesn't necessarily have a direct connection to astronomy. So I'm not quite sure where that came from. But I was interested in astronomy and in college studied physics, but became really interested also in the history of the field. And at about the time I was finishing my undergraduate degree, there was a predicted glut of astronomers. And going to graduate school, I've been thinking about that, about getting a Ph.D. in astronomy, becoming a scientist. I decided that if I was going to be an unemployed scholar, then I'd like to go study the history of astronomy. That glut of astronomers, by the way, turned out to be a poor prediction. Actually, the field has grown enormously. I don't know how many others were discouraged from entering astronomy, but in my case, I'm not unhappy about that because I came to Wisconsin. Wisconsin had one of the most important history of science departments in the country, and I came here to study the history of astronomy in the University of Wisconsin History of Science department. And that's been great because I found quite quickly then lots of connections in the astronomy department that have always worked well, both for my historical interests and also as a place where I could apply the history of astronomy for teaching and outreach and things like that. So it's really been great.
Can you talk to me a little bit, just briefly, about some of the classes that you teach at the UW?
Sure. The astronomy department has quite a wide offering, of course, because we have an advanced graduate program, but it's closely connected to physics. And I don't teach any of those advanced courses because I'm really a historian, not a scientist. So I teach introductory astronomy, and then I teach the course called Astronomy 206, which is also History of Science 206. It's cross-listed in the two departments. And that's the history of astronomy and cosmology. So I teach that course that attempts to cover from antiquity to as close to modern astronomy as I can get us, which is usually falls off somewhere in the early 20th century. And then I do a quick lecture at the end about space astronomy, and then we're out of time. But
so why is that an important thing to understand, like the history of astronomy? Why does that matter? The history of science in general? Why is it important to kind of look back and think about those things?
Yeah, well, I for some of the same reasons I was saying earlier, but I think it's important for any undergraduate who gets a bachelor's degree here to go away with some understanding of the role of science in the world, and that's why we have requirements. Even your English major has to take some science, and just part of as a liberal arts background. And as I was saying earlier, astronomy has, not only does it have some appeal, but it's often called the oldest of the sciences, which in a retrospective sort of view is true. We can look back 2,000 years and find people doing what we call astronomy. Oh yeah, that guy's doing astronomy. Science itself was not really what we would call science today. But still, it has this historical sweep that, say, organic chemistry doesn't really have, or something along that line. Not to pick on them particularly, but just that long history helps a lot. But of course, then that has been accompanied by these remarkable changes in the way people see the universe and our relation to the universe. And so, for that reason, what's often called the scientific revolution, the pivot in the way we see humans' place in the universe that takes place around the really the Copernican worldview, that ties in so many important things about how humans think about nature at the empirical level and at the theoretical level and at the level at which these things interact with society and politics, and that at first glance might not even seem like they ought to be part of the same history course. The Reformation, for example, the growth of universities, things like that. In that way, the history of astronomy is sort of a way to think about how people think about their place in the universe and how much that can change, and the reasons why it can change, or at least the reasons that we see historically speaking of why it's changed. How can one generation see themselves as the center of the universe, and another generation see themselves as inhabitants of a planet with more in common with the way we see ourselves than the way their grandparents saw themselves? Those kinds of things are fascinating to explore, and so I think astronomy offers a great deal of that, even if it weren't for the importance of science to our society and the need for an educated public in that way. I still think the history of astronomy would be a fascinating subject. There'd still be a lot of books on it.
Speaking of books, you wrote a book called Between Copernicus and Galileo, about a guy named Christoph Clavius. If I'm saying somewhere close to saying that correctly, you can correct me in a second. But it's a book about a figure that is largely forgotten to history, probably for most people. Who was he, and kind of what interested you enough to write that book?
Right. Well, Clavius, Christoph Clavius, that's usually how it's said. Although if you watch 2001: A Space Odyssey, I think they pronounce it Clavius. The crater that's named after him on the moon plays a role in 2001: A Space Odyssey. Clavius was an interesting guy. He was a critic of Copernicus. And I got interested in him at first when I recognized that the astronomy that he was teaching looked very medieval, but the date of his books was in the early 1600s. And I wondered kind of what was going on here. Why is he still teaching this stuff? I really got interested by looking at just the illustrations in the book. And but he turns out to have been interesting in a number of ways. Not that he was any kind of a great scientist or anything. He wasn't Galileo and he wasn't Copernicus, but he was an interpreter of both to generations of European college students, because his textbooks were widely printed and widely used, especially at Jesuit universities. The Jesuits operated a very large and influential system of universities in Europe, well, really around the world, but primarily in Europe. And he was a Jesuit. He was writing the mathematics and astronomy textbooks for the Jesuits in that period, in the late 1500s. And so I kind of went into a study of him, in part because I was curious about just his place in the history of astronomy there, in this period when Copernicanism is becoming an important factor in astronomical thinking. This guy is still defending the old geocentric system, and I wanted to see how
that the Earth was a center of the universe.
Yeah, that the Earth is stationary at the center of the universe. well, why is he still saying that, and how is he defending that in a period when more and more people are thinking there might be something to this Copernicanism stuff? And he lived just long enough to learn of Galileo's first observations with the telescope and to have some of his younger colleagues verify those observations with their own telescopes, and to publish in the last edition of his textbook a short recognition of Galileo's work, and to observe that astronomers are going to have to, I'm paraphrasing rather liberally here, but astronomers are going to have to change some things in order to deal with what they're learning. And so in that last textbook, he, without ever converting to Copernicanism or anything along that line, he gave a pretty clear evidence that he saw the future coming, saw that this was going to change things. And really it is. The telescope, Galileo's application of the telescope to astronomy is, one can certainly argue, the beginning of modern astronomy. And so Clavius has this interesting place. So I wanted to look at his critiques of Copernicus. What's wrong with Copernicanism? One of the things that was kind of interesting was that when you read his book, he was concerned that Copernicanism that a lot of people saw it as a valuable sort of thing, but he was much more incensed about some other alternative cosmologies that nobody remembers anymore. It was not this dichotomy sort of thing, but there were really a bunch of cosmologies sort of competing that ranged not just across like structural issues about what's orbiting what, but also intellectual issues. How much can we actually know about the heavens? And there was a continuum in that direction too, of people who maintained that basically we could know nothing about the heavens, to people like Clavius, who thought that you could derive real knowledge about the heavens based on just the observations that you can make. And he thought they led off in this one direction, and he actually would have agreed with Copernicus that you can derive knowledge. He just thought Copernicus had made a big mistake that way. But those two would have been at odds with the people who said you can't ever reach any conclusions about what's really going on in the heavens. All you can really do is just map these things and make up tables, and that'll allow you to predict when you'll have a full moon or an opposition of Mars. But you won't ever know what's actually happening out there. So to look at the intellectual ferment of that period, and now I'm still just talking about astronomy. It's greatly informative about what's happening in society more broadly, the Protestant Reformation and Counter-Reformation being a big deal, of course, and these things fit into these broader social currents in ways that illuminate them.
Famously, Galileo, who is not forgotten to history at all, made many contributions to human understanding of the world, and was famously labeled a heretic for it, and lived a lot of his later life home arrest, basically. So how does your work kind of studying Clavius and Galileo and kind of the evolution, as you were saying, from one generation to the next of the understanding of knowledge, you see connections through the course of time to our current era? I'm just kind of curious what your perspective on that is.
Well, that's a deep one. Well, I mean, certainly there are connections.
We talked about flat earthers, but there's also just the questioning of climate change and things like that in our modern day society. I mean, I'm just wondering how, things like that, when you see flat earthers or you even see people questioning climate change, does it make you think about Galileo and some of those issues that he dealt with?
Well, yeah, I mean, it certainly makes me wish that more people had some understanding of why we do things the way we do. I often wish that people had a little better knowledge of the history of astronomy. It's a history of science more generally, and it's there at the level of my best available working hypotheses and my best available and applicable evidence, and my best ability to make some testable predictions. Those are at a very deep level. That's what somebody has to be doing some work in a scientific sort of way. And if we understood science a little bit better as a society, I think we might have a little bit better insight into how we digest the results that are presented to us and whether they make sense or not. And earlier you mentioned flat earthers, for example, and we could trot out all kinds of other wacko kind of ideas that are out there that get a lot more attention now than they might have. I don't think wacky ideas are any more plentiful than there used to be. They're just transmitted much more easily. And not so long ago, to get your wacky idea out there, you'd have to have published a pamphlet and handed it out to your friends or something. And evaluating claims that people make, at least claims about nature. I mean, there's all kinds of other things you can talk about where science really is no help at all. Theology comes to mind. There's no experiment you can do that's going to tease out one theological claim from another. If so, it's no longer theology; it's science. But when we're talking about nature, claims about the world, one way or the other, there are ways to approach these things. But it's like I was saying about the flat earthers a little bit earlier. You really have to be in it. You can only really have a discussion with them if they too are motivated by a search for what's true about the world, or what's our most reliable knowledge about the world. I'm just trying to be philosophical there. We may not ever reach the truth in some absolute sort of sense, but we can reach better. We can refine our understanding about the world. But if you're not really interested in that, if what you're interested in is undermining people's confidence in whatever they've been taught or whatever that they've been doing, or if you're just interested in having an argument or something along that line, then the history and that sort of thing is probably not going to help. It's going to be more a matter of getting people having a discussion with the same goals before you can ever make any progress there. Whatever it is that makes people enjoy an argument so much seems sometimes to motivate the stuff more than any search for knowledge about the world.
Yeah, that's an interesting point. So I want to talk a little bit about the UW Space Place. Just can you tell me a little bit about some of the things that you have going on here and what your kind of enduring mission is here at the UW Space Place?
Sure. So Space Place is part of the UW Astronomy Department, and our primary goal is space science and astronomy education. So we do that a number of ways. We have a number of public programs that we do, programs for families and children on every Saturday at 10 a.m. I have a colleague who's very talented educator, comes up with fascinating hands-on projects and attracts audiences every Saturday. We have speakers on various subjects that once a month on the second Tuesday of each month. These are all on our website, of course, which is pretty easy to find, spaceplace.org. We also have programs about what's currently happening in the sky. So we do that once a month as well on the third Friday of each month. And we combine that with stargazing, weather permitting. We have some telescopes that we can open up. We also do programs around town and really around the state, park programs. In fact, the astronomy department has a program called Universe in the Park, which is not a Space Place program, although we collaborate with the Universe in the Park crews a lot. That's mostly the graduate students in the department. But we also, Space Place, does programs in parks, especially around Madison and Dane County. We give talks about what's currently happening in astronomy or on the history of Wisconsin astronomy. I've given a few talks on that here and there to community groups and things. In addition to those sorts of science programming, we're also a little bit of a museum. And so we have a number of exhibits about modern astronomy, sort of the role of various aspects like studying different parts of the electromagnetic spectrum or something along that line, which complement, of course, the kind of astronomy that's been done here, which we also have here in artifacts, various instruments that the University of Wisconsin has built and used in space astronomy applications. A direct descendant of the OAO instruments was one of the first instruments on the Hubble Space Telescope. which we have here which was brought back to Earth after the first shuttle servicing mission. And we have a number of other space payloads that have flown on exhibit, and we also have our historical exhibits as well. We've talked a good bit about the history here, and so we have some artifacts and display material on the history of Wisconsin astronomy.
In a lot of ways, you're the public face of the UW Astronomy Department. In a lot of ways, through the UW Space Place, through you're kind of a conduit to the public in a lot of ways for media. And I'm wondering what you make of being kind of that public face for UW Astronomy, and just as a conduit to science and scientific study. How do you feel about it?
Well, I take it pretty seriously. But to some extent, I try to just be, I think you said the word conduit, but I try to make connections, because there are researchers, not just in the astronomy department, but around campus who are specialists in pretty much anything that somebody would approach me about, except the historical kind of stuff. So I can generally at least I can try to find somebody who really is an expert on, if it's black holes or the Big Bang or whatever it is. But I think it's an important sort of thing for a number of reasons. I care very deeply about how people think about science and that sort of thing. And so there are things to be learned from that, even from fairly common sorts of events like lunar eclipses. There's a nice lunar eclipse every couple of years on the average. If you really think about that, there's a lot to be learned from that. I'd love to be standing next to one of those flat earthers when that happens. And so, what do you think is happening right now? I think I know what I think what's happening now, but explain this to me anyway. So you see where I'm going. But so I try to handle those various sorts of roles as much as to be a connection back to the science, as well as being an interpreter of it with my own then historical takes on it here and there.
There's so many moments, a lunar eclipse, which happens fairly often, things like that, the total eclipse 2017. There's always these moments or opportunities that can really put a lot of things in perspective for people and kind of stoke their interest. So, I'm just thinking about me as a kid, things that happened that got me interested. So there's so many opportunities it seems like, for you to be able to make a difference in somebody's life, in a little kid's life, and kind of alter the course of what he's interested in or she's interested in the future. Do you think a lot about that? Because I'm sure there's a lot of kids that come through here, the UW Space Place, and you have opportunities to interact with young people. Do you think about those opportunities as really things that can make a huge difference in their life?
Well, yes. I think you have various levels of success. Sometimes somebody looks through a telescope at Saturn and they say, "Wow, that is the coolest thing I've ever seen." And it's stimulating to them, and maybe they want to know more. And the occasional one looks through there and said, "Oh, is that all that is?" I thought I've got a picture on my calendar at home that's better than that. Well. So I'm not ever even things that seem like they ought to be great moments aren't necessarily always, but you just keep on tossing them out there and hoping that they take. I do think that looking through a telescope is a fundamentally different sort of experience than looking at an image on a computer monitor, even though you can see a better, or at least a more spectacular or more detailed image of a galaxy or whatever. But when you look through that telescope, it's those photons that left that galaxy 2 billion years ago that are now going into your eye. It's a different sort of relationship with what's in the sky. You don't have to. You're literally gathering the light up yourself there and seeing whatever that is. And sometimes the instruments themselves produce a more intimate relation with the universe. A telescope is actually a fairly simple thing. And so we've got some ones that are handleable by kids, and they're just completely open. You can talk about how this thing works. They can see the parts and they can experiment with it a little bit. And you hope, anyway, go away with a feeling that they can manipulate an instrument like this to investigate nature. And so you kind of hope that somewhere back there, they're thinking, this is something I'm intellectually capable of, and it's interesting, and the technology is there for me to play with and learn from. So it's great when you have those moments and you know it. And it's a little bit disappointing when you have those moments but then there's so many out there where, it may not be just that moment that somebody exclaims that it's the most wonderful thing that's ever happened to them, but they may not say anything and still go home thinking about it. And so you have to hope that happens most of the time.
I'm wondering if you can think of a moment that you've had maybe with somebody over the course of your career and kind of opening up space for them.
Earlier in the summer, I had a group up at Washburn Observatory, and we were looking at Mars, fairly close to opposition when it was near its maximum, at least for this time around, maximum size and brightness. And Mars is one of those things that when you first look at it in the telescope, you see a reddish, yellowish kind of disk. And you see the disk. But there's detail there that doesn't jump right out at you. It varies from time to time, of course. But so a lot of times people just look and then they move on. But occasionally you can get somebody to stick with it, especially if there's not a lot of time pressure and it's a smaller group or something. You could say, okay, just hang on there and keep looking. Look around the edge. Look for differences in shading between the center and the edge, and compare the top to the bottom. And then, and this did happen one of those nights, a young woman's looking in there and she says, "Oh, why is there a white sliver right there at the top? Is that the telescope?" And I said, "No, you've seen the southern polar cap of Mars. But that doesn't jump right out at you. You got to study it for a little bit because they're just subtle shadings, really. And they'll happen faster for some people than others, but the eye and the brain kind of begin to parse these things out if you just slow down and take it a little bit at a time." And she was pretty excited by that. I was too. I thought that's really cool. She just usually it takes, a few tries. So those kinds of things happen, but that's when there's something subtle like that to be teased out that somebody's not expecting, and then they bring it out, then they discover this on their own. That's really cool. That's got to be a lot like what an awful lot of astronomers discovering things. That's funny, not a eureka kind of thing, but what is that kind of response? And then it might turn out to be something pretty cool. So anyway, those are great experiences, but they're always fun.
Thanks to Jim Lattis, it was fun to chat with him about all the cool things that he does. I spoke with him quite a while ago, but glad to finally get this interview online. Make sure to subscribe to the podcast on iTunes, Stitcher, or Google Play. You can also stay in the loop about the pod by visiting wispod.com and following the show on Twitter @WisPodcast and on Facebook @The Wisconsin Podcast. Cheers.